Is my screen visible?
Yes, sir.
Okay. So let's start today's session. So good evening everyone. Today is your problem solving session 10 and I'm your TA Vidushi. So let's start by solving some of the questions. So the first question is the efficiency on energy transfer is related to the distance between donor and acceptor molecule as it does not depend on the distance. It is inversely proportional to the distance. It is inversely proportional to the sixth power of the distance or inversely proportional to the fifth power of the distance. So basically, how can you relate the energy transfer efficiency and the distance between donor and receptor? So what will be the answer?
Inversely proportional to the sixth power of the distance.
Yes. As we have discussed, like energy transfer efficiency is equals to R naught 6 divided by R naught 6 plus R 6. So this energy here it is energy transfer efficiency, and this is your the distance between donor and acceptor. And what is R naught? R naught is the Foster radius.
Foster radius.
And what does Foster radius indicate? What is Foster radius? When the energy transfer efficiency is
50%
50%.
between receptor and donor.
Yes. So the answer will be inversely proportional to the sixth power of the distance, as it is inversely proportional to this. Now next question. Fluorescence lifetime does not depend on temperature, quencher, concentration of the fluorophore or the structure of the fluorophore. So what is fluorescence lifetime? So fluorescence lifetime is the time when a molecule, like how much time a molecule is in excited states. When a molecule absorbs light, it goes to excited state, and the time it stays in the excited state is the fluorescence lifetime. The time the molecule has spent in the excited states before coming back to ground state is the fluorescence lifetime. So we discussed that it doesn't depend on Like we've discussed in a previous class also, like fluorescence time does not depend on temperature, quencher, chlorophyll concentration, or chlorophyll structure.
Concentration.
Correct. It with the fluorescence lepton does not depend upon the chlorophyll concentration, while it can depend on various external factors like temperature, pH, etc. Next question: which of the following compound does not fluoresce? Like that means they're asking which does not show fluorescence. So it is polycyclic compounds, or is it conjugation with electron with donating groups, compounds with multiple conjugated bonds, or non-planar compounds?
Non-planar compound.
Non-planar compounds, because like how can we say that a molecule is a fluorescent molecule? It should be rigid.
Rigid.
It should have shorter.
Lifetime.
Correct. And there should be conjugation and many more. So the answer will be non-planar compounds. Now, next question. Energy transfer efficiency when measured, the fluorescence intensity of the donor in presence and absence of receptor area are 0.4 and zero point 0.8 respectively. So what is the energy transfer efficiency? Is it 0.85, 0.2, 0.68 or 0.5?
0.5.
How? How it is 0.5? 0.5 is correct.
1 minus 0.4 upon 0.8.
Correct. So we know energy transfer efficiency, that is it is equals to 1 minus fluorescence intensity of donor acceptor divided by fluorescence intensity of donor. So in the question they are telling the fluorescence intensity in presence of acceptor. Like with donor in the presence of acceptor it's 0.4, and in absence of acceptor, that is they're talking about donor only, so it will be 0.8. So 1 minus 0.5, it comes out to be 0.5. So correct answer will be 0.5. Now, fluorescence spectroscopy, the intensity can be increased by photodecomposition, electron withdrawing group, increase in temperature, or increase in viscosity. So how can you increase the fluorescence intensity?
Increase in viscosity.
Yes, it will be increase in viscosity. And why it is increasing viscosity? Because like how can viscosity increase the intensity? As if we will increase the viscosity, then the collisions of the molecule will decrease, and due to that the intensity will increase. So that's why fluorescence intensity get increased by increasing viscosity. Now the next,
Ma'am, what is photodecomposition, madam?
photodecomposition. They are asking like intensity can be increased by, but if photodecomposition can occur, then intensity will decrease.
Okay.
Yes. And static quenching. Next question is about static quenching. So static quenching is due to complex formation of the fluorophore in the ground state with a quencher, complex formation of the fluorophore in excited state with a quencher, transfer of energy from the fluorophore in the excited state to the quencher, or transfer of energy from the quencher to the fluorophore in the ground state. So what will the answer? Why does static quenching occurs?
Option A.
Option A, correct. It will be complex formation of fluorophore in the ground state of the quencher. Like we discussed in a previous session that quenching is decrease in the fluorescence intensity. That is called quenching, and it can be collisional quenching, it can be static quenching, there can be self quenching also, or it can be chemical quenching. So we discussed like in collisional quenching what happens is that it occurs due to the interaction of the quencher molecule with the excited molecule of the fluorescent species. While in static quenching it occurs due to the complex formation in the ground state. So this is the difference between collisional and the static quenching. So just remember, static quenching occurs in the ground state, collisional quenching occurs in the excited state. Now, which of the following is not true for frat? So what is frat? Frat, F-R-E-T.
You need the full form or to explain it.
Like, firstly you can tell the full form of frat.
Foster resonance, fluorescence resonance, energy transfer.
Yeah, it's correct. It's Foster resonance energy transfer. So we know that what happens in the frat is that the emission of the donor overlaps with the absorption of the acceptor. That is, there is a spectral overlap. Second, we discussed that the distance should be less than 10 nanometer. Then we discussed that dipole orientation should be optimum for an efficient flat. Here what happens is that the donor's fluorescence is quenched and acceptor's emission gets depolarized. And you know that what happens is that, like, if you just excite a donor, then this donor emits the light and acceptor takes it and further emits the light. That there is an energy transfer between donor to the acceptor molecule. So that's where the acceptor's fluorescence will enhance due to the donor's excitation, and also the donor lifetime is shortened in the frat. So like in the first option they are telling in frat study the lifetime is of longer. So it's wrong. Frat can be measured by film. And what is film? Film is the fluorescence lifetime imaging. It's correct. Frat can be measured by fluorescence polarization microscopy. It is also correct. And in fact, acceptor's emission is depolarized. It's correct. So they were asking but is not true. So in frat study the lifetime is of longer. So that is wrong. So the right answer will be the first option. Now moving to next question. The incorrect thermodynamic relation among the following is delta G is equals to minus RT log n K. Delta G equals to RT log n K. K equals to Fu slash Fn. K equals to U slash N. So it's
Second option.
second option, because delta G is equal to minus RT log n K. So this will be your wrong option. Now next question. In light harvesting complex, the fluorescence of a chlorophyll molecule is quenched by nearby chlorophyll molecules. Given that for a pair of a chlorophyll A molecules, the R naught here is the Foster radius. It is 5.6 nanometer. So by what distance should two chlorophyll A molecules be separated to shorten the fluorescence lifetime from 1 nanosecond to 10 picoseconds? So they're asking about the distance between the donor and the receptor molecule, the R1. When they are separated to shorten the lifetime from 1 nanoseconds to 10 picoseconds. So how you will calculate the R here? So how you calculate the distance between them? R naught is given, lifetime is given, distance you have to calculate.
Small r.
Yeah, small r you have to calculate.
Tau is equals to r naught to the power 6 by r naught to the power 6 plus small r naught to the power 6.
As you know, like the energy transfer efficiency is equals to R naught 6 divided by R naught 6 plus R6. This you have to calculate, this you know, and this you also do not know that, and the energy transfer efficiency value. So firstly you will calculate this. Like how can you calculate the energy transfer efficiency? You know this formula, 1 minus fluorescence lifetime of donor and receptor divided by lifetime of donor only. So what's the lifetime of donor and receptor? It's 10 picoseconds, and with alone donor it's 1 nanosecond. So it will be 1 minus 10 picoseconds. So you will convert it into seconds, and for donor it's 1 nanosecond. So after solving it, it can come 1 minus 10 minus 2. That means 0.99. So now you know the value of N. That the energy transfer efficiency is 0.99. Now if you'll just put the value of energy transfer efficiency in this formula, then and R naught, you know, it was 5.6 nanometer. R6 now you can calculate. So just solve it. Five point six raised to by 6 is 30840.9. So after solving it, R raised to by 6 will be 311.52. So your R value is 2.5 something, so that means 2.6 nanometer approx. So it should be 2.6 nanometer, so that their fluorescence lifetime will be reduced from 1 nanosecond to 10 picoseconds. So that distance will be 2.6 nanometers. Is it clear? Is it clear to everyone?
Yes, ma'am.
Okay. Now the next question is the percentage transmittance of an aqueous solution of disodium fumarate at 250 nanometer is 19.2% for 5 into 10 raised to a minus 4 mole per liter solution in 1 centimeter cell. Calculate the absorbance A and molar absorption coefficient E. In second part, you have to calculate what will be the percentage transmittance of a 1.75 into 10 raised to a minus 5 mole per liter solution in 10 centimeter. So just tell me for the first part what will be the value of absorbance.
Two minus log T.
2 minus log T, okay. But do you know the transmittance value? It is percent transmittance.
0.192.
The absorbance comes out to 0.194. It's wrong.
And the transmittance would be 0.192.
Okay. Just tell me what will be the value of absorbance. You can simply also apply I equals to log I naught by I. So it can be log 100 divided by 19.2. So after solving it 0.717. It comes out to be 0.717. So absorbance value is 0.717. Is it fine? Now in the second part, you have to calculate molar absorption coefficient E, or that is molar absorptivity. That means how strongly a molecule absorbs the light. You know that A equal to ECl, where A is the absorbance, E is the molar extinction coefficient, C is the concentration, and L is the path length. So you have to calculate E. That comes out to be A divided by Cl, and your absorbance value is 0.717, concentration is 5.5 into 10 raised to a minus 4 into 1 centimeter. The length is 1 centimeter. So solve it and you will get the value of molar extinction coefficient.
14.3 into 10 to the power 2.
Yeah. And remember to write units. It will be liter per mole centimeter. Is it clear? Now for the second part, what will be the percentage transmittance? Like concentration is given and path length is given. Now you have to calculate the percentage transmittance. So how you will solve it?
Log inverse of absorbance.
Correct. Just apply the formula and just tell me the percentage transmittance.
Point 144.
Point?
144.
Wrong. They ask me percentage transmittance.
Ma'am, absorbance we should not take then 0.717.
No.
We should take in percentage, ma'am.
Correct.
19.2. That we should take, ma'am.
There is no need to calculate. Like for these questions separately, you have given concentration and path length, and you can just take, like if you just use this formula, so you know that molar extinction coefficient was 1.4 that you have calculated from the first question. Path length was 10 centimeter, and concentration was
5 into 10 power minus 4.
I have written wrong. Concentration is 1.75 into 10 raised to 5 minus 5, and path length was 10 centimeter. Like this is given in the question, 1.75 and 10 centimeter. So from that you can easily calculate log I naught by I. So just solve it, and after solving you will get value of I naught by I. It will be 1.78. Now you know that percentage transmittance. What is the formula for percentage transmittance? It is simply, you can write 100 I by I naught.
Yes, ma'am. Reciprocal of.
Yes. And directly just put the value and just tell me what will the percentage transmittance after it by solving it.
56.17.
Correct. 56.1. See, what happens is that, like, you know that A equals to ECL, but earlier in the first part you calculate the absorbance with different path length and different concentration. That's why you were not using absorbance for the second question.
Okay. So we are again just finding out the absorbance and taking log inverse.
Yeah, because you know that percentage transmission, for the percentage transmittance you need the value of I by I naught. So for that reason
Yes,
you,
ma'am.
you just put, yeah. Now the next question: in water the fluorescence quantum yield and the observed fluorescence lifetime of tryptophan are 0.20 and the lifetime is 2.6 nanoseconds respectively. So what will the fluorescence rate constant? Quantum yield is given and lifetime is given. So just you have to calculate the fluorescence rate constant Kf. So what's the formula for the fluorescence rate constant calculation?
F naught by F is equals to 1 plus KQ tau naught concentration of quencher. That formula, ma'am.
But you haven't provided with that concentration. You have been provided with quantum yield and lifetime. So there's one direct formula. So what's the relation between quantum yield and lifetime and the rate constant? You know that quantum yield is the emissive rate of the fluorophore divided by emissive rate of fluorophore plus non-radiative rate, and what is lifetime? It is tau equals to 1 divided by Kf plus Knr. So
Yes,
fluorescence
ma'am.
rate constant is quantum yield divided by fluorescence lifetime.
Tau.
So now quantum yield is 0.20 while lifetime is 2.6 nanoseconds. So just convert it into seconds, multiply by 10 minus 9. So after solving it will be
7.6 into 10 power 7.
correct. Approx 7.7 7%. Is this clear?
Yes, ma'am.
Now next question. Consider a study of the protein rhodopsin. When an amino acid on the surface of rhodopsin was labeled covalently with the energy donor 1.5-1 edens, the fluorescence quantum yield of the label decreased from 0.75 to 0.68 due to quenching by the visual pigment 11-cis retinal. Calculate the distance between the surface of the protein and the 11-cis retinal, where R0 is given 5.4 nanometer for the 1.5-I edens divided by 11-cis retinal pair. Basically, you have to calculate the distance between the surface of protein and the pigment. So, what will be the answer? Like the same question we have discussed in the starting slides. So how you calculate the distance? You know this
R
formula?
naught to the power 6.
Yeah, you know this formula R0 6 divided by R0 6 plus R6. And you know, for this calculation, for the distance between acceptor and donor calculation, you should know the value of Foster radius and energy transfer efficiency. Value of R0 is given, it is 5.4 nanometer. So you have to calculate the value of energy transfer efficiency. And just see in the question what is given. You have been provided with fluorescence quantum yield. So just apply this formula. Quantum yield in donor receptor divided by in the presence of donor only. So it will be 1 minus 0.68 divided by 0.75. So it comes out to be 0.093. Is it clear? Now you know the energy transfer efficiency is 0.093. Now simply apply this formula. So what will be the value of R? Just solve this.
8.185 nanometer.
8. It will be approx 8 nanometer. I think to be precise it will be 7.9 nanometer. Now we will solve one more question. Suppose you have been provided with fluorescence quantum yield of 0.16 and fluorescence lifetime of 1.5 nanoseconds. So what will the value of K? What will the value of this rate constant? Yeah, I have been provided with fluorescence lifetime, that is 1.5 nanoseconds, and fluorescence quantum yield, that is 0.16. So what will the rate constant value?
From 0.16 divided by 1.5.
Correct. It will be 0.16 divided by 1.5, and it is in nanoseconds, so you multiply by
10.6 into 10 power 7 per second.
correct. So that's all. Now we will start with a new topic, that is about NMR spectroscopy. NMR spectroscopy. So what does NMR stands in the NMR?
Nuclear magnetic resonance.
Correct. It is nuclear magnetic resonance. In today's session, we will discuss only little basics of the NMR. While in the next session, we will completely the session will be on NMR, and there is some questions related to NMR. So, how can you say that a nuclei is NMR active? So, what are the conditions for a nuclei to be NMR active? You might have heard like some of the nuclei are NMR active, some are NMR inactive. Like we discussed in IR, it was IR active or IR inactive on the basis of dipole moment changes. So in NMR also there are some nuclei that are active or some nuclei are NMR inactive. So what are the conditions for a nuclei to be active? Firstly, it should be charged. And you know, like if you will see proton, boron, carbon, nitrogen, oxygen, fluorine, every nucleus is charged, because you know that in nucleus there are protons and neutrons, and neutrons is neutral, it doesn't carry charge, but protons carry positive charge. So you can say every nucleus is charged, so you can't differentiate whether among these who can be anywhere active or inactive on the basis of charge. So second criteria is it should have a known zero spin number. So this is the main criteria by which you can distinguish that NMR is active, that particular nuclei is active for NMR or not. Non-zero spin number, that is I. I, you denote by I. I is your nuclear spin. If your nuclear spin is 0, or it can be nuclear spin is not 0, and that is non-zero, this one, then never active one. So how you will know that it is 0 or it is not 0? If the mass number is divisible by 4, then you can say I will be 0. Suppose for carbon 12, you know, like for a element we represent, suppose if we represent some element by x, here we represent atomic number and here we represent mass number. So Z is your atomic number, A is your mass number for any element x. So here it's 12C, that means mass number is 12. Also you can easily divide by 4. So as mass number is divisible by 4, therefore for 12 carbon, like 12C, the I will be 0. So we can say the 12C is NMR inactive. Is it clear? Like you might have heard, like we do NMR for 1H NMR, 13C NMR, but we have never used 12C. Why? Because it is NMR inactive. Now if you will see, tell me, like if it is 14N, just tell me whether it will be NMR active or not. Nitrogen with the mass number 14.
Active.
Active. Why? Because if you will divide by
Not
4, it is not divisible.
non-zero.
Yeah, it is non-zero. So what are the examples that a nuclei have non-zero and 0? So you just remember this table, nuclei. Uh, just tell me about 28 silicon. It is NMR active or inactive?
Inactive.
Inactive,
Inactive.
correct. For 19 fluorine, fluorine with a mass number 19.
Active.
It will be active. And 16 oxygen. Oxygen mass number 16.
Inactive.
It is inactive. And you can also write it as non-magnetic. While another part is I, that is not equal to 0. that is your magnetic nuclei. And now, what is the example? It can be 1H, 13C, 19F.
Ma'am, 16 is not divisible by 14.
16 is divisible by 4, no? 4 4 is 16. That means it is NMR inactive. Because
Inactive. Okay, ma'am.
yeah. Now you know that this value,
Yes, ma'am.
like this, is NMR active part.
Active. Okay.
So here you can further divide the magnetic nuclei into two parts that have a nuclear spin half or that have nuclear spin greater than half. So the nuclei which have nuclear spin half or spin number half, that are called as non-quadruple nuclei. Non-quadrupolar nuclei, and which has greater than half, it's quadruple, or you can simply say ellipsoid nuclei. And what's the difference between these two? Like in case of non-quadruple nuclei, you get a sharp signal, while in quadruple you get very broad signal. And what are the examples for the quadruple nuclei? It is 1H, 13C, 19F. By non-quadruple nuclei can be deuterium. As in deuterium, the I value is 1. 14 nitrogen, it's also 1. For 11 boron, it's 3 by 2. So these all are the main nuclei that we will talk about. And generally we discussed about these nuclei only. Mainly about these, like proton, carbon, fluorine, nitrogen, phosphorus, and in non-quadruple, as I value is 1 for deuterium and nitrogen, while for boron it's 3 by 2. Now here in quadruple also we can divide into two parts. It can be concentrate nuclei or it can be dilute nuclei. What does concentrate and dilute means? So the example in the concentrate 1H, 19F. while in dilute it can be 13C. So what happened is that in concentrate nuclei, its natural abundance is more. That's why they're called concentrate nuclei. In dilute nuclei, abundance is less. Like in proton or 19, like in proton, it will be near about 100%. While for fluorine, it's 100% natural abundance. While in 13C, it is 1.1%. As you know, carbon can naturally carbon can exist in as 12 carbon or 13. So there can be two different isotopes. So 13C exists in 1.1%. So this 100 minus 1.1 will be 12C. Is it clear? Is it clear?
Yes, ma'am.
Now you know the magnetic nuclei are that has a nucleus spin 0 and non-magnetic that has I non-zero. Oh, it's I non-zero. And non-magnetic as I 0. And further, the magnetic nuclei can be quadrupolar or non-quadrupolar. In quadrupolar nuclei, you get a sharp signal, while in non-quadruple, you get a broad signal. Secondly, in quadruple nuclei, your spin number is half, while in non-quadruple nuclei, your spin number is greater than half. And what are the examples of quadrupolar? It is proton 1H, 13C, 19F, 15 nitrogen, and 31P. For non-quadrupolar, it's deuterium, and for deuterium, the I value is 1 for 14 nitrogen. Now you may see like nitrogen can be in 14N, or like there are two isotopes, or can be 15N. So for 14 mass number, like nitrogen with 14 mass number, I is 1, and for 15 it is half, and for boron it's 3 by 2. Now further, in quadrupolar nuclei, it can be concentrate nuclei or it can be dilute nuclei. And in concentrate nuclei, it consists of those nuclei which exist more in nature, that natural abundance is more, like proton. So in proton, the natural abundance is nearly 100, while in fluorine it is 100%. And if you just see for the dilute nuclei, its example is 13C and it is 1.1%. Also, if you have seen that if we give sample for 1H, so we need very less sample, and it also it takes very less time for 1H, like it's approx 1.5 minutes or something. But if you will see for the 13C, it takes a lot of time and more sample is required to record 13C. Why? The only reason is that the natural abundance of 1H is more, that it is nearly 100%. While for the 13C, the natural abundance is very less, that it is 1.1%. Therefore, you required more sample and more time to record your 13C sample. Also, you can just remember one thing, that if your mass number is odd, so you can remember that I value will be half into n. So it will be integral of half when your mass number is odd. So suppose your n can vary from 1 to, it can be anything. And if your mass number is even, then your value of I will be a whole number. It will be 1, 2, 3 and so on. Suppose you are taking example of 14n. Now your mass number is even as it is 14. That's why I value is, if you will calculate, it is 1. Now if you look on 11 boron, your mass number is odd. So that's why for boron it's 3 by 2. Your n value is 3. If you put 3 into half, it's 3 by 2. Is it clear?
Yes, ma'am.
Okay. Also one more point you can remember, like in quadruple nuclei, it has a spherical nuclei. And we know, in non-quadruple it is ellipsoidal nuclei, like something like spherical nuclei, and here it will be ellipsoid, something like that. So suppose 31 phosphorus, now just tell me what will the mass number, like the mass number is odd or even? It is
Odd.
correct, it is odd. That means it should have I value, it should be integral of half. So for 31 phosphorus, I value is half. Like for deuterium, its mass number is odd or even?
Even.
Correct, even. So even, it means it will be a whole number. So its I value is 1. So now what happens in the NMR? Like the absorbed photon it promotes the nuclear spin from ground state to excited state. As you know, energy levels are degenerate. Energy levels are degenerate. Degenerate means, what does degenerate mean? Means like energy. What is degeneracy in the energy level? Equal energy, na? So suppose if you are not applying any magnetic field, not applied, then you know the two levels are degenerate. Means suppose if you have 1000 molecules, then 50 will be here, 500 will be here, and 500 will be here. This is the condition when your magnetic field is not applied. But now you are applying some magnetic field. You are applying some magnetic field. So what happens is that now there is no longer degeneracy. The degeneracy is break. So the levels will be well separated. So some molecules are here, some will be here. So there will be transitions from here to here, from this state to higher energy level. So transition will be up to that when the population of the both energy level will be same. So up to when the population of the energy level will be same, then only transition will stop. And transition will occur up to that time when both energy level will be same. Population of both energy level will be same. And more transition means more signal intensity. Is it clear? Is it clear? Now, am I audible?
Yes, ma'am. Can you start now from first?
Maybe I will start it again. Like up to this, is it? It was well understood now. Like if mass number is odd, then I is integral of half, and if mass number is even, then I is a whole number. Up to this, it was clear.
Yes, ma'am.
Yes.
Yes,
So
ma'am.
maybe this I will repeat. The Boltzmann distribution I will repeat again. You know that the energy levels are degenerate. that is energy level are degenerate. Suppose if magnetic field is not applied, if there is no magnetic field, then the energy levels are degenerate. Suppose what did degenerate mean? Suppose if you have 1000 molecules, then 500 will be in this energy level and 500 will be in this energy level. So basically these two levels are degenerate. But if you, when you apply some magnetic field, you are like, for magnetic field you denote by B. So suppose if you are applying some magnetic field, then your degeneracy get break. Then earlier it was 500 molecules in the ground and 500 molecules in the above energy level. Now it will be, maybe it can be 1000, it can be 600 here or 400 here. So there might be some degeneracy, will be break here. So what happened? If you're applying some magnetic field, that degeneracy will break. So energy levels will be well separated. So there will be some molecules here, there will be some molecules here, and the one molecule will undergo transition to above, then this another molecule simultaneously, and this transition will happen. So this transition will happen up to that when population of both the levels will be same. The moment the population gets same, that it reaches to 500 and 500, then there will be no transition. Up to that the transition will occur. So basically, what is Boltzmann distribution? There are two energy levels that are degenerate, and suppose you have 1000 molecules. So 500 will stay in the ground level and 500 will be in the upper level. As both the energy levels are degenerate, there is no much difference in the energy. And this was the condition when you are not applying some magnetic field. But when you apply some external magnetic field, then this degeneracy get break. So there will be that two energy levels will have different number of molecules. So more than 500 molecules will be here and less than 500 will be here, and there will be transition of one molecule, then second molecule, like that. It will not occur simultaneously, it will occur one by one. Like firstly this molecule will get in the transition state, then the second will go. No, like two molecules will not go together, it will happen singly. So this transition will occur up to that when the population reaches same, that is there will be 500 here and 500 here. Is it clear? Is it clear?
Ma'am,
Yes, ma'am.
without magnetic field also it is like 500, 500 same only, no, ma'am.
Now please repeat.
Before applying magnetic field also it will be same, like
Yeah,
500,
before
500.
magnetic field it was degenerate. Both the energy levels were closed. They were
Okay.
degenerate. But if you apply some external magnetic field, then this degeneracy get broken, and there will be separation in the both energy levels. Suppose firstly there might be that there is 800 molecules in the ground E1, and in E2 energy level there will be 200 molecules. then one by one the molecule will get to E2 energy level, and the moment when the population is same, then the transition will stop. So transition happen up to that time when in both the energy levels there are same molecules, same number of molecules.
Okay,
Like,
ma'am. The
yes.
main aim is to prevent degeneration.
So like you know that in animal we use radio frequency. So you are applying some radiation and the molecules are moving to higher energy level. And remember that the more will be the population difference. Like here and here, the more population difference, or you can say more transition, more will be the intensity. More will be the intensity. Now we will discuss like about the instruments. Like in NMR you might have seen NMR instrument, and you know, like it can be 600 megahertz instrument, it can be 400 megahertz instrument, or it can be 200 megahertz instrument. So there is difference in frequency. Like the NMR instrument can be 600 megahertz, can be 400 megahertz or 200 megahertz. Also remember that this may vary. Your frequency is directly proportional to the magnetic field. So just to remove this proportionality sign, we use a constant gamma by 2 pi into P naught. And what is gamma here? Gamma here is the gyromagnetic ratio. Gamma here is the gyromagnetic ratio. And just remember the gyromagnetic ratio for proton and carbon. For proton it is 42.5 megahertz per Tesla, and for carbon it is 10.70 megahertz per Tesla. So your frequency is directly proportional to the magnetic field. So frequency is gamma by 2 pi into P naught. And the gyromagnetic ratio of proton it is 42.5. That means your energy gap or E is directly proportional to frequency and is directly proportional to your gyromagnetic ratio. Is it clear? Is it clear?
Yes, ma'am.
And can you
Yes,
state
ma'am.
the gyromagnetic ratio? What is that?
But actually gyromagnetic ratio is that ratio of magnetic moment to its angular momentum. And just remember, for proton and carbon only, like gyromagnetic ratio of proton it's 42.5 and for carbon it's 10.70. Like if you will ask that how can you divide the sensitivity of NMR spectroscopy, so you can tell about the sensitivity on the basis of instrument. Like if the instrument is 600 or 400, so as 600 is more frequency, so that means 600 is instrument will be more sensitive if you will compare with 400 megahertz. Secondly, by nuclei, like 1H, it has more abundance, natural abundance. So if you will talk about the sensitivity of the NMR, like the sensitivity of the NMR, so you can explain on the basis of the instrument and the nuclei. If you will see like in NMR, it can be 400 megahertz, it can be 200 megahertz, or it can be 600 megahertz, or so on. Out of these three, the 600 megahertz will be more sensitive, and in nuclei, suppose 1H, the natural abundance of 1H is approximately or nearly 100%. So if you will compare the sensitivity of the instrument for NMR, you can tell on the basis of instrument and the nuclei. And that frequency here, this frequency, it is your Larmor frequency. So next we can solve one question. So what will be the Larmor frequency? Larmor frequency of proton in magnetic field of 1.41 Tesla, suppose. Provided gyromagnetic ratio is given. So like this type of question, you can directly solve by simply applying the formula frequency, the Larmor frequency equal gamma B naught divided by 2 pi. So from here, by this formula, you can easily calculate the Larmor frequency. Is it clear?
Yes, ma'am.
Okay. So basically for the NMR, firstly you will see that the nuclei is active or not. So first for that criteria, there are two things, charge and non-zero spin number. And you know the every nuclei are charged because in nucleus they consist of protons. So you know, like for 1H, if we start with the basic nuclei, the first one, that is proton. Proton consists of one, like 1H consists of one proton, and proton is positive. You have some charge here. Now second will be helium. So you know every nucleus is charged. So by this you can't distinguish whether nuclei is NMR active or not. The second criteria is non-zero spin number. Non-zero spin number, that is it should not be equal to 0. And now you have divided the nuclei into two. Those nuclei that are magnetic nuclei with the I value 0. That are NMR inactive nuclei. And how you can tell whether it is non-zero or 0? If mass number is divisible by 4, then it is non-magnetic, that is I is 0. And if the mass number is not divisible by 4, then it is magnetic nuclei, that is I is not equal to 0. And in case I is not equal to 0, they are further divided into two, quadrupolar and non-quadrupolar nuclei. In quadrupolar nuclei, the value of I is half, while in non-quadrupolar, the value of I is greater than half. And in quadrupolar, you get a broad signal, while in non-quadrupolar, you get a in quadruple you get a sharp signal. No, it was just a second. Shit. It should be non-quadrupolar here. And it should be quadrupolar. Should be quadrupolar here. Non-quadrupolar nuclei have I equals to half, and quadrupolars have I greater than half. And in non-quadruple you have a spherical nuclei. You have a spherical nuclei, while in quadrupolar you have a broad nuclei. Example of non-quadrupolar are 1H, 13C, 19F, and for quadrupolar it's deuterium 49. And then further the quadrupolar are divided into two, concentrate and dilute. Concentrate nuclei are those nuclei which have more natural abundance like 19F, 1H, while dilute nuclei are those in which natural abundance is less Like in 13C it is 1.1. Then we discuss about Boltzmann distribution. Suppose if you're not applying some magnetic field, that both the energy levels will be degenerate. But if when you are applying some magnetic field, the degeneracy get break, and if there will be more population difference, it corresponds to more intensity. Now sensitivity, how you will tell about the sensitivity. So for NMR you can tell on the basis of two nuclei or instrument. Suppose your instrument is of 400 megahertz and one instrument is of 200 megahertz. So 400 megahertz has more frequency, therefore it is more sensitive instrument. Then on the basis of nuclei, how can you tell about sensitivity? Like since the lateral abundance of proton is more, so it is more sensitive. Now there is a relation that Larmor frequency or the frequency is directly proportional to the magnetic field. So to remove the proportionality sign, you write gamma by 2 pi, where gamma is your gyromagnetic ratio. So remember that energy is directly proportional to frequency or the Larmor frequency and is further directly proportional to the gyromagnetic ratio. And the gyromagnetic ratio of a proton is 42.5 and for carbon it is 10.7. And you should know this formula to calculate your Larmor frequency if you have been provided with some magnetic field. In gyromagnetic ratio you know that for proton and for carbon. In NMR, like to record an NMR samples, we use a reference. And what is the reference for NMR? What is the reference for NMR? TMS. TMS, tetramethylsilane. Why we use this TMS as a reference? Because all the protons, it has 12, 3 plus 3 plus 3 plus 3, it has 12 equivalent protons. It is inert, that is not reactive. It is volatile. So that's why we use TMS as a reference for NMR. I'm just telling you some basics of NMR. More details we will discuss in our next session. But this reference, sensitivity, Boltzmann distribution, this you should know before going deep in NMR.
Ma'am, in Boltzmann distribution,
Yes.
initially the energy gap was less, and
It
uh,
was same, like
they
it
are
was
in
not
degen.
degenerate. Yeah, it was degenerate. It was same energy gap, same energy levels.
But when magnetic field is given, so, the energy level increases, and this will
The
be
degeneracy break.
until the
Uh,
degeneracy break. And then again, the degeneracy level will be maintained. Means after means until you said
not
no that both the
degeneracy. You
level
can't
have
say
same.
degeneracy will be. Degeneracy will stay. Degeneracy is energy level should be same. Energy levels should be high only. Like there will be separation. Like basically, what happens is that when you're not applying magnetic field, then the energy levels are same. All the energy levels are same. That is degenerate. When you're not applying some magnetic field. But if you apply some magnetic field, then this degeneracy get broken, and due to that, the two energy levels are separated. But they like for this case, there will be like suppose there are three molecules here and two molecules here. Now it is degenerated. They don't have the same. So up to that time in which this energy level and this energy level will have same molecules, up to that time the transition will occur. So at the end it will be like same molecules here and same molecules here. But you can't say that degeneracy will stay. It is not degenerate. Energy levels are not same. I'm just saying if external magnetic field is applied, transition will occur. So you are providing a radio frequency, so there is some transition. But transition will occur up to that time when the molecules in the both energy levels are same. Degeneracy is what? That energy levels have the same. Energy levels have the same energy. Your energy is not same after applying magnetic field. Only we are talking about the number of molecules. And only at one
Okay,
time
ma'am.
one molecule will be transited to the above energy level. Not two molecules will go. One by one molecule will go to higher energy level. So that time when molecule reaches the same. Suppose you are having initially 100 molecules. Now 27 are here. 67 are here. And 33 are here. But at that time when there are 50 here and 50 here, that time up to that time the transition will stop. Otherwise, one molecule will be here, then it will be 34, then again it will transit, then will be 35. Up to so on the transition will occur. The moment it reaches 50-50, like the same or equal number of molecules, then the transition will stop. But you can't say it is degenerate. Degenerate you can say in terms of energy levels when they have the same energy levels. The energy levels are different only. Is it clear?
Yes, ma'am.
Okay. So that's all for today. But so we have discussed about energy transfer efficiency. Just remember, like there are 2-3 formulas by which we can calculate energy transfer efficiency. It can be equal to 1 minus, if in terms of lifetime, it can be lifetime of donor and acceptor divided by lifetime of donor, or you can simply say in terms of fluorescence intensity also. 1 minus fluorescence intensity of donor receptor divided by fluorescence intensity of donor. also it can be equal to R naught 6 divided by R naught 6 plus R6. That is, the energy transfer efficiency is inversely proportional to the 6th power of the distance. Then about lifetime, that fluorescence lifetime is independent of the concentration but depends on the external factors like temperature, pH, etc. or the quencher. And then we discuss like what are the conditions for a molecule to be fluorescent. It should be rigid, it should have conjugated pi electrons, conjugated system, it should have pi electrons, it should be planar. So non-planar compounds will not fluoresce. Then for fluorescence intensity, it can be increased by increasing viscosity. Why? Because the collisions of the molecule will decrease. Due to this, the intensity will increase. Then we discuss about the quenching. That quenching is the decrease in the fluorescence intensity, and it can be static quenching that occurs due to complex formation of fluorophore with the quencher in the ground state. Then collisional quenching, it occurs due to the excited state. Then there can be concentration quenching, that is due to some self quenching. And there can chemical quenching. So basically quenching can be four types: chemical, cell, sulfur concentration, static, and collision. Then we discussed about FRAT. That FRAT is the Foster radius, Foster resonance energy transfer. That there should be a spectral overlap. Transition dipole should be optimum. Distance should be less than 10 nanometer. Lifetime is not long. Its lifetime is not longer in the FRAT. So the first option was wrong here. And the FRAT can be measured by fluorescence lifetime imaging, or it can be measured by fluorescence polarization microscopy. And in FRET, the emission of the donor gets quenched and the acceptor's emission is depolarized. So the acceptor's emission is increased due to the donor, and the relation that was wrong was delta G equals to RT log n K. Then we discussed like how the fluorescence rate constant is related to the quantum yield and lifetime. That is, fluorescence rate constant is ratio of quantum yield to lifetime. Then we discussed like we have to calculate the distance between the surface of the protein and the pigment, but you are provided with the fluorescence quantum yield. So you know that energy transfer efficiency is R naught 6 divided by R naught 6 plus R6. R6 is the distance between the donor and the acceptor. This you have to calculate. So firstly you will calculate the energy transfer efficiency, and then you will put the value of Foster radius, and then you can calculate the distance between donor and the receptor. Then we discussed about NMR. That NMR is a nuclear magnetic resonance spectroscopy. Basically in this spectroscopy, for an NMR to be active, it should have a non-zero spin number, and then further these nuclei can be magnetic or non-magnetic. Further, magnetic nuclei have I non-zero, and it is further divided into non-quadrupolar and quadrupolar. Non-quadrupolar means I is half, and quadrupolar means I is greater than half. Non-quadrupolar have a spherical nuclei. Quadrupolar have a ellipsoidal nuclei. Sharp signal is observed in non-quadrupolar, and a broad signal is observed in quadrupolar. Then they further into concentrated and dilute nuclei depending on the natural abundance. If the abundance is more, then it is concentrate, and if it is less, then it is dilute. Why 13C has a 1.1% natural abundance? Because carbon can available or exist in both forms, 12C or 13C. Since the natural abundance of 13C is 1.1, and for carbon it will be 100 minus 1.1. Then we discuss Boltzmann distribution and how can you see NMR sensitivity. We can tell about on the basis of nuclei. Suppose proton, it has a natural abundance more, so more sensitive. Or we can see on the basis of instrument. Suppose if in some institute there is 600 megahertz instrument and in other institute it is 400 megahertz institute. So in that institute which has more frequency like 600 megahertz, that will be more sensitive instrument. Then frequency is directly proportional to your magnetic field, and so there will be one formula that frequency is gamma by 2 pi into B naught, where gamma is your gyromagnetic ratio, and for the maybe in the numericals you might have use of this gyromagnetic ratio of carbon and proton, so you should remember it. That is for proton it is 42.5 megahertz per Tesla, and for carbon it is 10.70 megahertz per Tesla. Then we discussed about the reference, like for NMR we use a reference that is TMS, that is tetramethylsilane, that is a Si with 4 methyl groups. So total there are 12 equivalent protons, and why we use it as a reference? Because it has 12 equivalent protons. It is inert, that is not reactive. Also it is volatile. That is the reason we use TMS as a reference. And it is the internal standard also. So that's all for today. Any doubt?
Lecture.
Yes,
Excuse me,
Vaibhav.
ma'am.
Yes.
Ma'am, lecture notes week from week 4 it has been not uploaded in the portal, ma'am.
You can directly write to the instructor for that.
We have written, but still no action has been taken, ma'am. Because PPT notes will be helpful for us during assignments and exam revision, ma'am. Till week
Yes.
3 it has been uploaded, ma'am.
Up to week
From
3 it
week
is okay.
yes, ma'am.
Any further doubt related to session?
No, ma'am.
So now the basis of NMR is clear. Like what happened, like if you provide a radio frequency, like we discussed, there are in electromagnetic spectrum we discovered X-ray, UV, IR, and so for NMR we use radio frequency wave. And what is the basic of NMR? So is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. So thank you.
Thank you, ma'am.